To explain 7, we have to go to the torus. The torus is one of the most common phenomena in nature. For example, the vortex in air, the tornado, is a vortical or toroidal motion. Again, eddies in water. The magnetic field is toroidal in shape. The torus or vortex shape has the unique property that it's the only thing that can sustain itself and is the only thing that is made out of the same substance as its surroundings. In other words, you can have a tornado which is made out of nothing but air, and the tornado is in air. If you were to try to talk about how to explain a universe from nothing, the toroid shape or vortex would really be the only one you could call on, because if you said, well, it's spherical, then in order to have it made out of the same substance, not have two different things like a sphere of putty and a lot of air, you would have to say that, well, there's a condensation of fog in the middle of the fog, but that condensation would rapidly dissipate. Whereas a torus or a vortex, it's like a smoke ring, will continue to exist even though it's made out of air in air. So we have good reason from a purely physical point of view to give special attention to this vortex or torus. However, there's a much more impressive reasoning to me that the torus is the shape that the universe must have, which is that it's the only way you can explain a number of metaphysical problems. Perhaps the oldest of these problems is how can there be free entities in a universe run by God? While relativity has no reference to God, the same problem comes up. How can you have the discontinuities of quantum theory within the continuum? It's like if everything is cake, how can you have raisins? In other words, the dichotomy between the particularity of the raisins and the generality of the continuum or the cake remains a dichotomy. And you haven't really got to the bottom of things until you've explained the dichotomy in terms of one thing. Well, for this, the torus offers the solution, and the solution is as follows. Suppose if I had a plane, just imagine a plane surface, and there's a dot or a man on the plane. Then I make a cut all around the plane and separate that piece of the plane. Then I've separated the man from the rest of the plane. I've separated this entity from the rest of the universe. Now, this would be either or proposition. Either that man or that piece is part of the plane or it's separate. You can't have both. But with the torus, you can have both. And let me show you how that would be the case. Here's a little blemish that I could call a man. Can you see that all right? I'll make it a little more definite by putting a line around it. This represents some unique entity that's all by itself. But of course it's connected with everything else. The only reason you say it's by itself is I've just drawn this line, but that's just ink. It's not, it's still connected. But suppose I cut around it with this brown line. Now I've cut all around it. The only difference I've made is that I've included this hole. Of course, this hole can be infinitely small, and the whole thing can be compressed down. But the principle involved is that I make one cut all around this entity. Now, you'd have to imagine my unfolding this from the brown line, separating it all out, and you see that this thing would still be connected to everything outside the brown line, because you could go around through the hole and come up again on the other side of the fence. Here's the fence all around, but I can still get from here to any place outside the fence by going through the hole. In other words, this entity is connected with the hole and also separate from the hole. I call this pseudo-separation, and it's that pseudo-separation we have when we create the ego. In the third stage, the separation was represented by a circle with a dot in the center. It was the principle of identity, the principle by which this thing can be given enough distinctness to be able to say it has identity and is distinct from its surround. But it's only a pseudo-distinction because, as we see from this going through the hole, it's still connected. Connected, as it were, by a sort of umbilical cord. Now, we can't expect this umbilical cord to be a visible thing the way this microphone line is, where I'm connected to the sound system or the lights are connected to the power lines. The umbilical cord is non-physical. It is in those two upper levels that we said were projective, the two upper of the four levels. Well, let's look a little more. What else does the torus tell us about this universe? Agreeing that it's a possible and even preferable model because it complies with these requirements that we mentioned. Well, this brings me to the coloring problem. The coloring problem is a basic characteristic of surfaces. In fact, I can show in this diagram two orders of surfaces already. Imagine that this first figure, this one and this one, is a line rather than a surface. I've given it width so I could clearly show areas. But think of this as just a ring. Now, to make distinctions on the ring, I need three colors, because in this one where I've drawn three things, each one touches three and also two, two touches three and one, three touches two and one. So I need those three colors. That's the way it's shown here. If I'd introduced a fourth area, let's say where I've made these dots here, call that 4, then that is not touching, I could use the same, it's not touching 1, so I could use the same number, 1. 1 for this and 1 for this. And since I've also removed the contact between 3 and 2, I could color it with just two colors, 1 and 2. So I don't make it more difficult by adding this area, I make it simpler. And if you explore, you'll find that only an odd number of sections will require 3. An even number of sections will require only 2. Now suppose we go from this, which is a line going around a circle, to a plane. Here's a plane, and I've divided it in 3 segments as before. And if I were to try to stick in a fourth one, again, I would have separated, I would have created a situation where I could color both this and this with the same color, and this with the same. So instead of using 3, I'd only need 2 colors. So I don't exhaust the possibility of coloring by this process of making more segments. However, moving to this diagram, if I put a place in the center, then I have to have 4 colors, because you notice that 4 touches 1, touches 2, and 4 touches 3. Similarly, 1 touches 2, 3, and 4. And as before, if I were to stick in an extra one and try to say, well, I'll need a 5th color, I've separated it so now that I could color 2 here as well as here, and this 3 and 1 could be the same, so I'd only need 3 colors. So we get to the theorem that more than 4 colors is not necessary for a plane. This is the famous 4-color theorem. I don't know whether it's been proved now or not, but no one has ever succeeded in making a map that requires more than 4 colors. You'd think it would be easy to prove, but you see there's always some joker who comes in and says, well, let me put a country in here, and then you find you have to recolor the whole thing. Now the problem is, can you prove that whatever this other person does, you will still be able to color it with 4 colors? That proof may have been done by computer, but it hasn't been done in any clean, simple fashion. I don't like to leave it without mentioning that I believe this 4-color problem for the plane is equivalent to what I outlined in both the geometry of meaning and the reflexive universe, that there need be no more than 4 levels, no more than 4 distinctions, 2 dichotomies to describe any situation. Doesn't mean that that's enough for a universe, but it means it's enough for a mapping, that is to say, a description of that universe. Well, then comes the torus. And the torus has the unique property that instead of 4 colors, like this, and I should also say that the sphere is like the plane, it requires no more than 4 colors. The torus requires 7. Now, as I roll this around, you'll see there are 7 colors, and that each color touches every other color. Now, maybe that's too much to see all at once, but if I stop for a minute, suppose I take yellow. On one side is purple, another orange, and here's the gold, here's the green, here's the red, and here's the blue. So there's 6 colors touching the yellow, in other words, 7 colors. And that's the same wherever I turn. If I take the purple, then it's outlined by blue, by green, by the gold, by red, and then we find on the other side by yellow and orange. So there's 6 colors around the purple, and this proves the 7-color problem. Well, what about colors? That's just a trivial thing, one could say. Well, it's not a trivial thing. It's a very profound. You can replace it by the problem of connecting points with lines that do not cross. And you'll find that only on the surface of the torus can you connect 7 points with lines that don't cross. It's the same as the coloring problem. Now, what this really means is that the torus, or topology of the torus, the surface that has this 2 ways that it goes around, provides the possibility of more kinds of interrelationship than the sphere. and is therefore, from that point of view, ideal for a universe. Now, this takes us into a rather long excursion to describe these properties that emerge. See, what I'm talking about is that the colors are not merely colors. There are interrelationships, and interrelationships are very important. Let me go about this in a leisurely way because it's a rather complex subject and you'll get all mixed up if I don't lay some groundwork. For that purpose, I have this chart which begins with the simple. These are the four levels according to the theory of process. And as we described before, the first principle is represented by the point, the second principle by the line, the third by the 3 points or plane, because 3 points determine a plane. 3 points also determine a circle, which is another way of representing this third principle, the principle of identity that I referred to just a minute ago. Then we come to 4 points, 1, 2, 3, 4, which when joined create the tetrahedron. It's like a pyramid. This is the base, this is the apex. The dotted line is the line behind. That's the first solid figure. It's a figure in 3 dimensions. So we're down to the universe in which we're living, this universe of objects. And I think I mentioned in the Reflexive Universe that we go further, when we can go further with more dimensions. But if I continue with this representation, that is to say point, line, plane, solid, then I get a figure that doesn't have any name. It's a figure that would be impossible to have in physical space. Because there are 5 points, each pair joined by a line. That means that even to draw it, I have to represent one of those lines, well, actually represent 2 of them dotted. See, but suppose it were in ordinary space, then it would be like 2 tetrahedrons base to base. See, here's the base, and this is the vertex of one, and that's the vertex of the other. Well, that's all very well. That's a very clearly a solid figure with 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. And every edge joins 2 points. But what about the top point and the bottom point? You see, in order to join them, I have to have an edge that's in the interior of this figure. That's the one shown by the dotted red line. Now, if you were making this out of pieces of equal length, you would get along fine until you came to that last one. That last one would have to be stretched. It's has to be longer than the others. Well, even if they're not the same length, it's impossible in practice to make that figure with this extra diagonal without causing what's called redundancy. In other words, the position of these 2 points, the top and bottom, is overdetermined. The lines around the outside are telling it to be in one place, and this vertical line is telling it to be in another. Now this in structures, as I said, is called redundancy, but it causes an internal stress in the structure, and it's very dangerous. You have to be careful to design a structure so that it's not overdetermined. It's not redundant, because it can even break itself. That's why bridges are supported on those roller things, so that they're free to move due to change in temperature. You don't want to determine the thing too much, because then it'll break just by the change in temperature. In this case, this figure could have so much stress in it that it would break before you put any load on it, so it'd be useless as a structure. On the other hand, we can look at this in a positive way and say this is a way of storing energy. In other words, think of this as a spring. This red line is a spring. We can now stretch the spring and store energy. This could be a sort of diagrammatic model, a theoretical model of a mousetrap or a wound-up spring, something that's containing energy. But to apply it more generally, I say this is a model of a seed, because the seed contains energy, and this energy is what starts the seed growing, makes it possible for it to put out the first leaves and then draw more energy from the sun, and then of course it continues on with its growth. But the original seed had some stored energy in it. That's why we eat seeds, because we draw that energy, beans or oatmeal, things like that. Well, you recall that this fifth place was that to which I assigned plants, so it's quite suitable that the five-pointed, five-verticed figure, which I call the pentaverton, because I'm counting the vertices. Normally you would say pentagon, meaning you're counting the sides. But since one of these sides is concealed, and anyway there are 10 of them, I call it the pentaverton, just counting the vertices. Well, that becomes then a symbol or a way of describing the abstract principle of growth, a principle that can contain energy, can store energy. 4 is the principle that makes a structure. 5 is a structure plus contained energy. Now we can go on and ask, well, what happens when we move to 6? That's 6 points. It's either 4 around the middle and the top one and the bottom one, so that makes 6. But now we have to have 3 diagonals. We've jumped from 1 diagonal to 3 diagonals. I really don't know how to interpret that, but since I have animals here, it's very tempting to relate these 3 diagonals to a kind of multiple stretch thing. And it's this, the girdles are made out of 2-way stretch. This would be a 3-way stretch, that what the animal has to have in order to be able to move, because in order to move he changes his shape, and that means that something is stretched. In fact, you have to stretch in all directions to have this movement. There's some other things that are very interesting, but perhaps I better come back to them. I might as well follow the course, which would be to come to 7. Now, when it comes to drawing the picture of 7 points with all the diagonals, because when you one way to do it would be to put this 7th point right in the center there, and then you'd have 6 more diagonals, internal edges. And that would so complicate the drawing that you couldn't see what was what. So I'm going to try to do it in front of you so you can see what's going on. I hope I can make it more understandable instead of more complicated. I'm going to do this in a different way because it is simpler to draw, and I hope simpler to understand. I have a circle here with 7 points. Now, the problem is to draw triangles such that no two triangles share more than 1 point. This is also given as the problem of the committees. You have 7 people and you want to make 7 committees such that no 2 people are on more than 1 committee. No pair of persons are on more than 1 committee. Now, if I start out with my committees, or my sets of 3, say, suppose I started with 1, 2, 3, then the next one was 2, 3, 4, you see I'd overlap 2, I'd defeat myself right away. So instead of messing around to trial and error, the simplest way to solve this is to go 1, 2, and skip 3. So if I do that, I'll have this triangle. Then the next one, I'll go 2, 3, and skip to 5. Now, you see, I've complied with my rule because there's no 2 members in 2 triangles. As I go along, and this will get more complicated, the next step is that way. Oh dear. I'm already now got 3 on top of each other, so I'll have to make some way of distinguishing. I'll leave this one white, and then this one cross it this way. Now you see this? Dotted one is covering the striped one, and both are under the white one. I should have left those out there, but at any rate, bear with me. The next one will be 4, 5, 7. And the next one, 5, 6, 1. The next one, 6, 7, 2. And I've only got one left, is 7, 6, 3. I really should do this under everything, but I'll make it very clear. I've now got 7 triangles such that no 2 triangles share 2 points. And that is another version of the figure that would follow this one. But you can see how complicated it would be. I would really have to put in, see, have I joined every point to every other point? Yes, I have. I've joined every point to every other point, so I've complied with the rule here. And I did it in an orderly fashion so that you can see that I did it the right way. Now, I began to be curious, since there is one always expects when you find something mathematical that there be something in reality corresponding to the mathematics, and of course vice versa. But in this case, I of course was setting up a correlation between the 7 colors, these 7 colors, I mean the coloring problem here, those 7 colors were the 7 grand stages of process. But here's something else. This is the committees. These are interrelationships of three of these points, or three of the powers, and they should mean something. And I kept scratching my head about what these committees could mean. I could see no way of correlating them to anything I knew about. And then I remembered the thing I did before. I better just remind you of what it is quickly. I didn't prepare the chart. I took this circle and showed these three triangles. The three types of evolution. This is the Darwinian evolution, the DNA. This is from attraction through trial and error to the goal, which is instinct. And this is intelligent, seeing how the law works, recognizing what it is, light, recognition of the principle, and its characteristic of true thinking in the better sense of recognizing truth. Well, I had done that separately, without realizing, or it didn't occur to me that these are the triangles that were involved in this complicated picture. Well, how could I could then assign three of them, but how would I assign the rest of them? And that didn't come about until I realized that I was neglecting an important rule of process, which was that the whole thing is cumulative. It begins simply, and then it accumulates this, and this, and this, and this, and this. It builds on itself. It's cumulative. So that what I should do is make triangles as I go along. And if I think of starting with one, then I can't have any triangle, because there's only one point. Nor can I have anything with two. It's not until I get a three that I can create a triangle, and that becomes my first triangle, which could be the principle of identity that I referred to as emerging at the third stage. Now, when I come to 4, I can't make a new triangle because I'll include this whole side, and that's against the rule. So it's not until 5 that I can get another triangle. Then I get the one that corresponded to DNA. In other words, the idea here and the survival of the fittest, and the good idea becomes the prototype and evolves the DNA for the species. That was the DNA triangle. Well, then when I go to 6, let me see if there's another triangle that I can draw from 5. I don't think there is. I'm forgetting my own rules now. No. It's not until a 6 that I can now draw the triangle that corresponded to instinct, which was this one, from attraction to trial and error to instinct. But I can also draw now a new triangle that I didn't have before. That's this one. Five, 6, and 1. So I've got 1, 2, 3, 4 triangles at 6 points. I could put it here, 4 triangles. When I come to 7, of course, I have the one that represents human evolution, the recognizing the law. That's one more. Then I can join this and this and carry that I want to be sure I do this right because it's my last chance. I think it's this way. And the other one is this way. Now, you see, I've added 3 at the 7th stage. 3 added. Up to here I had 4. But the 4 I had plus the 3 gives me the 7 triangles, 7 committees. And these would be powers. Now, I'm really trying to talk about the abstract mathematics, so I don't have to say what these things mean. In fact, I don't even know what these last 2 triangles I put on mean, but I can account for the rest of them. First one gives the identity, then there are 3 that give the 3 types of evolution, and this one that was introduced by 5 must be the element of choice that comes in with animals, because, the one that began with 6, that was this one. See, it goes back to 1, and 1 is choice, so it adds choice to what the plant had before. Now that makes the only 2 unaccounted for are this 7, 6, 3, which I think is the motivation of structures, or purposeful use of illusion through forms, which would correspond to art, and this possibly this one is connecting the principle of organization with the raw energy, organizing raw energy into machinery. That's another thing that man does. Now, I offer that only tentatively, but see, what I'm trying to do is be able to account for more things by the mathematical principles. And from the point of view of present discussion of why 7, it isn't necessary to solve this now. But you see that 7 is by far the richest so far, because we didn't get any of these triangles until we got to 3, and then we didn't add any till we got to 5, then we got 2, and we came in with 6, we got 4, and then jumped 3 more at 7. Now, if you were to go to 8 points, you'll find it breaks down. I think I'll just have to let you try that for yourselves. If I had 8 points, it would break up into 2 sets. I couldn't follow this rule that every one of these points is related to every other point. Any 2 triangles share one member. That's one of the rules. These are all spelled out in the back part of the Reflexive Universe. Now, this really is one of the most powerful reasons of all for the 7, because if a universe was built on an 8-fold principle, it would split up. If it was built on a 6-fold principle, it wouldn't be possible to have the richness of interrelationship that the 7-fold makes possible, and the same way for simpler numbers. So I think that is about the most powerful. Unfortunately, it's quite complicated, but it's very interesting. Of course, you could say, well, it's all very simple. If the fourness is valid, then it takes 7 steps to go down and back through the 4. But I don't know that that's as convincing. It's not complicated enough to be convincing. There's one further one that I had never allowed myself because it just seemed too simple, which is this thing that everybody's done when you first start playing with a compass. You found that you can exactly lay out 6 equal circles around 1. And that in turn creates a larger circle, and you can have 6 of those around 1. And so on ad infinitum. It's a way of saying as above, so below. Because whatever is true in this larger is true in the smaller. I would draw 6 circles inside this, and a 7th in the center, and then each of those would have 6 and a 7th, and so on, ad infinitum. This is, I think, well, the reason I rejected this idea at first was that I'm drawing this on a surface, whereas we want to think about what's going on in at least 3 dimensions, maybe 7 dimensions, who knows, and maybe this kind of thing doesn't go on in 7 dimensions. Well, then I realized, and it took me a long time to get through this point, that no matter how many dimensions you have, a surface is a surface. And this is a property of surfaces. The 7 distinctions are, in a non-pejorative sense, superficial. You can write down these distinctions, but that's not the same as living through them. So but in spite of myself, I have to make a map on a 2-dimensional surface. And that's really what a surface means. It's the superficial approach. I'm not using it as I said, not in a pejorative sense. It's just that this is the mapping and this is the cost you pay for mapping. It's not the same as experiencing the thing in depth. Well, there's one more principle that I've left out, which in a way is the most intriguing, but it's also a little more difficult. Can we shoot this tetrahedron again? Notice that around each vertex there are 3 triangles. Okay? We move to this one. Around each vertex there are now 4 triangles. Now this one doesn't show it, but if I remember that the internal diagonal is there, there are actually 5 triangles coming from each point. See, I can count the 4 on the outside, but if I were to really lay it out, there would be not 4 but 5 because of this internal one. Now, here you can almost tell by sort of implication that there are going to be 6 triangles around each point. You see, it's implied by this diagram of circles, because if I drew points like that, you see that would be a triangle, and there'd be 6 of them. Now, since 6 fills up the 180 degrees, each triangle has a 60 degrees subtended angle in its between sides. So 6 times 60 is 360. I filled up the circle. I filled up the plane. I can't add any more triangles, even to these hyperdimensional figures, which I can't illustrate in 3 dimensions, because the surface would still contain only 360 degrees, regardless of how many dimensions it was in. Now, that says, it's another way of saying you can't go beyond 7, because the 6 around the 1 makes 7. It also has a very delightful or mind-blowing or something to think about feature that suppose you were making models. You might start out with this simple physical model, and this wouldn't have to be a tetrahedron, but anything I made out of solid objects would be a model using that dimensionality. Anything I made out of living objects would be this kind of dimensionality, involving, as I said, 4 triangles around a point. Anything I made out of this, which is the transformation model, would be 5 points around an apex. When I get to here, my model has extended to an infinite plane. It's an infinite plane, and yet it's not infinite, because outside of these circles are more circles going on forever, but this circle is duplicated somewhere else. Each one of these has a duplicate over and over, but such that it's separated from all the others so that you wouldn't get them mixed up. This is another reference to the as above, so below. Whatever the process is, there are 7 stages, just as we found with the arc, the sub-stages and sometimes even sub-sub-stages. Well, okay, now we're ready for the blockbuster. Having made this model, you wouldn't know whether you were inside the model or outside the model, because the thing is perfectly flat. In other words, if you could make this model, it would be a new universe. And I think that's a good place to stop.